Welcome to OB's Math e-Pathshala.
So let us check so our intention is to prove that 2. So this is our goal. That is, each hi is normally in H, and each x can be represented uniquely as x equal to the internal product h1, h2, hk. Now, it is a homomorphism. Why? Why it is a homomorphism? For psi of just h1, h2, this hi, this dot h1 dashed, h2 dashed, hi minus 1 dashed, hi dashed, hi plus 1 dashed, hk dashed. Then what will happen? Now since uh, since H is a group, so we must have, this is true actually. Uh, HK is KH if and only if HK is a subgroup. So using this for finitely many products, this one. So HK is a subgroup. So with the help of this, you will have psi of just doing this one h1 h1 dashed, h2 h2 dashed, hi minus 1 hi minus 1 dashed, hi hi dashed, hi plus 1 hi plus 1 dashed, hk hk dashed. Just using this theorem, because hk h1 dashed will be h1 dashed this. Yeah. So then it is h1 h1 dashed, h2 h2 dashed, hi minus 1 hi minus 1 dashed, and this part will be identity, and it is again hi plus 1 hi plus 1 dashed, hk hk dashed. So then by using the operation, so it is h1 h2 hi plus minus 1 hi plus 1 psi of okay, So it is H1 test. So it is H1 H2 Hi minus 1 E Hi plus 1 Hk dot H1 dash H2 dash 1 dash E Hi plus 1 dash Hk dash. So this is going to be, so this one is psi of H1 H2 Hk, and this one is psi of H1 dash H2 dash Hk dash. So this proves that psi is a homomorphism. So this proves that psi is a homomorphism. So now, if we consider the kernel of this homomorphism, that is kernel of psi, then what it would be? That is set of all those H1, H2, Hi minus 1, Hi, Hi plus 1, Hk, such that psi of this member H1, H2, Hi minus 1, Hi, Hi plus 1, Hk is the identity. Is the identity means the identity in group H1 cross H2 cross this one. So what is the identity of this group? This is actually so this identity is actually, so this is equal to U E E E, yeah, this one, because each one is a subgroup of the group G. So therefore, so this means that H1 H2 Hi minus 1 Hi plus 1 Hk, and this is H1 H2 comma Hi minus 1 identity Hi plus 1 Hk goes to E E E, and this proves that set of all those H1 H2 Hi minus 1 Hi plus 1 Hk, such that H1 H2 Hi minus 1 Hi plus 1 Hk, all of them are identity. So these are all identity except Hi. So this gives that set of all those Hi, which Hi's are in capital Hi. So that means it is capital Hi. So just by considering the ith index, we have proved that Hi actually is the kernel of this map psi of this map. So since it is a kernel, so it must be a normal subgroup. So this proves that Hi's are all normal in H. So it is a kernel. Now for the second one, that is given any x, you need to show that this x can be uniquely represented as this. Now since x belongs to H, now H is the internal product of H1, H2, Hk. So this x must have an expression of this form. Now we need to show that this H1, H2, Hk's are unique. So let us suppose that this small x has two representations, h1 h2 hk and h1 dash h2 dash hk dash. So our goal is to show that these h1 h2 hk's are unique. So just using the inverse of phi, since one holds, so the phi is an isomorphism from h1 h2 hk onto h. Now we consider the inverse map of this phi. So using the inverse map, you will see that, so using the inverse of phi, we see that, so this element will go to h1 h2 hk and this element will go to h1 dash h2 dash hk dash. Now since these are order pairs, so h1 must be h1 dash, h2 must be h2 dash and hk must be hk dash. So this proves the uniqueness. Uniqueness of the representation of small x belongs to H. So this proves that 1 will imply 2. Now 2 implies 3. So what needs to be shown? 2 implies 3. That is, 2 means HIs are normal and each x can be represented uniquely as this. And 3, for 3 we need to show that this one is common. So we don't need to show this again. H1 is normal in H. This is common for 2 and 3. Now we need to show that if H1, H2, Hk is E, then the only possibility is all of them are identity. So let us check. So let H1, H2, Hk is identity. This. So now if we consider the inverse of phi, then we see that, so this will imply that this element will go to H1, H2, Hk and this element will go to E, E, E. So since they are order pairs, so H1, H2, Hk, each of them are identity. There is no other possibilities. So 2 implies 3. Now what is 3 implies 4? So you need to check that this one. Since HIs are normal, this is common to both 3 and 4. So you need to check that HI and H1, H2, HI minus 1, I plus 1, Hk. So it has only common element identity. So let suppose that some HI is common to both. This. Let us suppose this. Now since this HI belongs to this one, so this HI must have a representation H1, H2, HI minus 1 and the ith term must be identity Hk. And this implies, now the left hand side can be represented as, first position is E, second is E, I minus 1th term is E, ith is I plus 1th is E, kth is E. But in the right hand side we see that it is H1, H2, Hi minus 1, identity Hi plus 1, Hk. But in 3, we have assumed that every element has a unique representation. So there may not be 2. So for that reason, so all of them are identity. E. So Hi is E. So the only element common to both is identity. Now the last portion of this theorem is 4 implies 1, and this will complete the proof. So let phi colon h1 cross h2 hk to h be the map defined in 1. Defined in 1 by, what was the definition? That is h1 h2 hk goes to the internal product of h1 h2 hk. Yes. So so you show that this phi is an isomorphism. This phi is a homomorphism first. Why it is a homomorphism? Now 4, using 4, what is 4? 4 is all the HIs are normal, and the common element for HI and H1, H2, HI minus 1, HI plus 1, HK, this is identity. So this is our assumption. So HIs are normal. So this fact can be used to prove that for all I not equal to j, we check that hi hj equals with hj hi. This for all hi belongs to capital Hi, and for all hj belongs to capital Hj. Now how could you do this? Now since hi hj both are normal subgroups in H, so this is our assumption. So observe that, just consider this element hj inverse hi hj. This element must be in capital Hi, since Hi is normal, and since it belongs to this Hi, so just multiply this with Hi inverse Hj inverse Hi Hj. uh, sorry. Sorry, this element is so since Hi is normal, so Hij inverse Hi inverse Hij is in capital Hi. Since Hi inverse is also in Hi, capital Hi. So Hij inverse Hij belongs to capital G. This is the definition using the definition of normal subgroups. That is G and G inverse belongs to N for all N belongs to capital N for all G belongs to capital G. Yes. So this implies N is normal in G. Even only. So this one. So this implies Hij inverse Hi inverse no, I was right. Sorry, I was right. This is I was right. Sorry. Hi, Hi inverse Hi, yes. So this belongs to capital Hi. And for the Hj, we will have Hi inverse Hj inverse Hi. So this belongs to Hj, and this implies Hi inverse Hj inverse Hi. Hj belongs to capital Hij. Just product of this with Hj. So since Hi, Hj both are normal subgroups, so this will happen. So and both of them will imply that together imply that Hi inverse Hj inverse Hi Hj. This element is common to Hi intersection H. But in 4 it is given that Hi intersection H1 H2 Hj Hk is the identity for all I not equal to j. Yeah. And from this one we can imply that Hi intersection Hj must be identity. There is no common element of Hi Hj. But we have found one element which is common to Hi and Hj. And this implies Hi inverse Hj inverse Hi Hj is the identity. So that is Hi Hj must be equal to Hj Hj for all I not equal to j. And with the help of this observation, one can show that the map phi, if we apply this map to two elements from the group H1 cross H2 cross Hk, so this will give that H1 H1 dashed H2 H2 dashed Hk Hk dashed, and then it is H1 H1 dashed H2 H2 dashed, HK HK dashed. So using this observation, we have H1. So it is H1 dashed H2, and the second one is H2 dashed H3, and so on. And the last one is HK minus 1 dashed HK, and it is HK dashed. So in this way, you can apply this observation. You will have, so this one will be H2 H1 dashed, this one will be H2 H3 H2 dashed, this one will be HK HK minus 1 dashed HK dashed, and then again apply the same procedure, and you will find that all these HI's will come forward. That is, it is H1 H2 HK, and all the HI dashed will go to the right. That is H1 dashed, H2 dashed, HK dashed. So it is phi of H1, H2, HK, and it is also phi of H1 dashed, H2 dashed, HK dashed. Yeah. So this shows that phi is a homomorphism. Now by definition it is onto. It is onto. So it remains to check that the function is 1, 1. So for this reason, we need to consider the kernel of this map. So kernel of phi. What is the kernel of phi? That is a set of all those elements, all those order pairs, ordered elements, ordered tuples. That is H1, H2, HKs, for which this map will, this element will map to identity via phi. That is, their internal product is E. But H1, H2, HK is E. So what does it mean? That is, H2, H3, HK will be H1 inverse, this one, the inverse of this. So since it is H1 inverse, so H1 inverse must be in capital H1. But H1 inverse is, it has been represented as H2, H3, HK. So it must be in H2, H3, HK. But our assumption is 4 is this intersection must include the singleton E. So that is, from this one, H1 is identity. So now if H1 is identity, then it is H2, HK is E, then again H3, H4, HK is H2 inverse, and apply the same process. You will find that H2, H3, all of them are identity. And this proves that kernel of phi is the singleton set E, and hence phi is 1, 1. So this proves, so hence H1, H2, HK, this is isomorphic to H with the help of this. So this proves, so this completes the proof of our theorem containing 4 statements, and each one will imply the other. Each one is equivalent to the other. So all these statements are equivalent. So if we suppose one of them, then it will imply the others. So with the in view of this theorem, you can define another important observation is that we may consider internal direct product of groups. That is, let H1, H2, Hk are subgroups of G. So H1, H2, Hk be subgroups of G, and let H is H1, H2, Hk. Then this H is said to be an internal direct product of H1, H2, Hk if one of the statements in the above theorem holds. That is, one of the 4 statements holds. Any one, because all of them are equivalent to each other. So you can assume any one of them to define this internal direct product of H1, H2, Hk. So we can write down it as if condition 1, statement 1. Statement 1 of the above theorem holds. Yeah. And this is called the internal direct product of H1, H2, Hk. Okay. Now note that since we assume that one holds, so that means the map phi from H1, H2, Hk to H is an isomorphism of H1, H2, Hk, H1 cross H2 cross Hk onto H. And so is their inverse. That is, so observe that the map psi colon H2 H1 cross H2 cross Hk defined by psi of H1 H2 Hk goes to H1 H2 Hk. Yeah. So this is an isomorphism. Of H onto H1 cross HK. And so note that HI bar. What is HI bar? That is the set of all elements, all set of all elements which is E, and in the ith position it is small hi, and again others are E, where small hi belongs to capital Hi. And this is a subgroup of H1 cross H2 cross HK. Because as it is isomorphic to HI. That is, HI is isomorphic, HI bar is isomorphic to capital H. Yeah. That is, for each capital HI, we can find a copy of capital HI in the group H1 cross H2 cross HK. So, note that if H1, H2, HK are subgroup of a group G, then their external direct product always exists. This can be written as remark that if H1, H2, HKs are subgroups of G, then their external direct product always exists. But if we concern about their internal direct product, then their internal direct product exists if and only if, so you must put a condition, internal direct product exists if and only if the above map psi is an isomorphism. Psi is an isomorphism, and in that case, just keeping in mind the statement 1 of the above theorem, so in that case, this internal direct product is isomorphic to their external direct product. So their internal direct product, so their external direct product and internal direct product are isomorphic. Yeah. So in that case, we simply call the product as simply direct product of H1, H2, HK. So in that case, so we call it simply as direct product of H1, H2, HK. Okay. So this ends our today's lecture.
Thanks for watching. Please subscribe, like and share.